Welcome to This Explainer. Today, we are completely cutting through the science fiction to demystify one of the absolute most extreme, mind-bending phenomena in the entire universe. We're talking about black holes. And trust me, the actual physics at play here are way more fascinating than anything you've seen in the movies. So think about this. What happens when gravity literally breaks the universe? What actually occurs when gravitational pull becomes so overwhelmingly dominant that the normal, everyday rules of space and time just snap? Well, that's the terrifying, awe-inspiring, and honestly, incredibly beautiful reality we're gonna explore right now. Section 1. Defining the cosmic monster. Okay, let's dive into this. At its absolute core, a black hole is a region of space where gravity is so impossibly strong that nothing, and I mean literally nothing, not even light, can escape. Now, when you consider that light is the fastest moving entity in the universe, its total inability to escape gives you a pretty immediate sense of the immense, almost incomprehensible power we're dealing with here. But how do they get there? Well, for stellar black holes, this whole process actually begins with stellar death. Picture a massive star that finally exhausts its nuclear fuel. Without that outward pressure pushing back, the star just collapses inward, triggering a massive supernova explosion that blasts its outer layers across the cosmos. And what's left? The remaining core undergoes a complete, catastrophic collapse, crushing all its mass down to an unimaginable density. Section 2. Anatomy of a black hole. Let's look inside the anomaly. Let's take a virtual journey to the center, starting right on the very edge, the accretion disk. As we get closer, we run into this violent, glowing halo of incredibly hot gas and cosmic dust that's just spiraling inward. The friction here is so intense that it heats this material to millions of degrees, creating this absolutely brilliant light show right on the precipice of total darkness. And this brilliantly illustrates the next step. Pushing past all that glowing matter, we hit the ultimate threshold, the event horizon. This is the absolute boundary beyond which nothing escapes. It is the literal point of no return. Once you cross this mathematical line in the sand, no amount of energy, no amount of speed can possibly overcome that immense gravitational pull. Finally, at the very bottom of this incredibly deep gravitational well lies the singularity. This is the central point where all that colossal stellar matter is crushed into an infinitely dense point. It's right here that our modern understanding of physics is pushed to its absolute breaking point. I mean, the standard mathematics of relativity literally just break down here. It's wild. Section 3. Types and formation. A massive family tree. Now, these anomalies span the entire history of the cosmos, and they vary wildly in scale. First, we have stellar black holes, which, as we discussed, form from collapsing stars. Then, you've got the heavyweights, supermassive black holes. These absolute giants contain millions to billions of solar masses, and they just sit right at the centers of most galaxies. We also categorize intermediate mass black holes. And finally, there are hypothetical primordial black holes, which scientists believe might have formed way back in the dense soup of the early universe. Section 4. Myths, Facts, and Discoveries. Let's clear up some misconceptions. You know, there is a very pervasive pop culture myth out there that black holes are basically these aggressive cosmic vacuum cleaners just sucking up everything in sight. But in reality, they simply have mass, exactly like a star does. If you were to magically swap out our sun for a black hole of the exact same mass, Earth wouldn't suddenly get sucked in. Gravitationally speaking, we would just continue to orbit safely. I mean, we'd be completely in the dark, but we'd be completely safe. But that raises a big question. If they're completely invisible and they aren't actively pulling everything in, how on earth do we actually find them? Well, we detect them indirectly by observing their extreme environments. Scientists track their intense interactions with nearby matter, kind of like that glowing accretion disk we talked about earlier. We observe their immense gravitational effects, literally watching them bend the fabric of space and time. Occasionally, we'll spot these enormous, incredibly powerful jets of high-energy particles being blasted from their poles. And amazingly, advanced observatories can now even detect gravitational waves, the actual ripples in spacetime created when two massive black holes collide and merge. Now, what's really interesting about this slide is that it wasn't until 2019 that humanity achieved the seemingly impossible. We actually captured the very first direct image of a black hole's shadow.
By networking a bunch of radio telescopes all across the globe to basically create one giant Earth-sized observatory, scientists finally gave a visual face to this cosmic anomaly that we'd only been calculating on chalkboards for a century. It was a massive historic achievement for human ingenuity.
Section 5, the ultimate physics laboratory. Why they matter.
So, the crucial point is that black holes are not just bizarre cosmic oddities. They're actually the keys to unlocking the fundamental laws of physics. They give us a way to study the fabric of space-time in extreme environments that we simply cannot recreate here on Earth. They're absolutely critical to tracking the evolution of galaxies, since those supermassive giants literally anchor their centers. And furthermore, they serve as the ultimate stress test for Albert Einstein's theory of general relativity. Think about it. If his mathematical models hold up around the extreme, chaotic environment of a black hole, they pretty much hold up anywhere in the universe.
As we wrap up this explainer, I want you to ponder the very boundary of human knowledge. If absolutely nothing escapes a black hole, what unfathomable secrets are locked forever inside that singularity? Are the fundamental laws of physics entirely different in there? Does time even exist at that dense core? The truth is, we don't know the answers yet. But that relentless pursuit of the unknown, that's exactly what makes studying the cosmos so deeply thrilling. Thanks so much for joining me on this journey. Keep looking up and keep questioning the universe around you.